Welcome everyone to the Design World webinar series, and thank you all for attending today's webinar, How to Make 3D Scan Data Processing Faster and More Powerful. The other title we have for it is 3D Scan to 3D Print, Design Innovations with Faro and 3D Systems, sponsored by Faro Technologies. We would like to thank today's presenters, Les Baker and Michael Mock, for being here today. I'm Leslie Langnaw, Managing Editor at Design World Magazine, and I'll be your moderator today. Just a couple of housekeeping details before we get started. If you wish to tweet about this webinar anytime during or after, you can use the hashtag DWWebinar. We will also have a question and answer session after the presentations, but you can go ahead and submit your questions at any time, and we will ask them when the presenters are finished. And finally, this webinar will be available afterwards at our designworldonline.com website, and we will also send all the registrants a link. So let me introduce to you today's speakers. The first speaker is going to be Les Baker. He is an applications engineer at Faro Technologies with more than 24 years experience in engineering and design, including 15 years of experience scanning for reverse engineering and design. Before joining Faro, Les worked in various engineering capacities within the electrical, plastics, automotive, and aerospace industries. Michael is a product manager at 3D Systems. He is an expert in 3D scanning, having used the technology for 9 years to reverse engineer or inspect thousands of parts. He has scanned and reverse engineered everything from rubber chickens to C-130s, working with a variety of 3D scanners and all the major software packages. So he has a wealth of experience with this technology to apply to any given project. As a product manager for 3D Systems, he is helping to make 3D scanning processing faster, easier, and more powerful. As I mentioned before, both of these gentlemen will be available to answer questions after the presentation. And so let us begin with Les.
Hello, everyone. Firstly, today's agenda. We'll start with an introduction to Faro, the company, its technologies, and how they can help you with your application. That will be followed by Michael with an introduction to 3D Systems and how the Geomagic suite of tools can work with and without 3D printing to empower your design tasks. That will be followed by a live demonstration of some typical scenarios, leveraging and reinforcing some key aspects of the Geomagic software. And then it will be back to Leslie for the wrap-up and a Q&A session. So welcome to this presentation of the techniques and equipment that allow acquisition of as-built data on critical and key characteristics of legacy parts and how that can be integrated with the development of new and existing products. Faro has been providing digitization equipment to industry for over 30 years. Starting initially with small single-point tactile units, the range has expanded to include articulating measurement arms, such as our edge and gauge. These have lengths from 4 foot to 12 foot and the ability to leapfrog in order to measure larger parts. The user has access to high accuracy tactile and non-contact measurement with feature-based and point cloud capabilities that are ideal for small to medium-sized objects. The Vantage, our laser tracker, can capture high accuracy tactile data up to 262.5 feet from a single position. Also able to leapfrog, it's the ideal tool for very large-scale metrology projects. Our laser scanners, like our Focus 3D, enable large scale, and we're talking about a range of about 800 feet from a single position, with the ability to leapfrog. Mass point cloud acquisition at a rate of around 1 million points a second allow very detailed photorealistic visualizations with the ability to extract measurements from the underlying point cloud. We also have our software solutions, CAM2 and Scene. These are our own award-winning metrology software, and our large-scale point cloud capture and manipulation software. There are many types of technology solutions on offer, which include white and blue light imaging systems. These usually require an independent method to place all separately captured images within the same coherent data set. This registration is typically done as a post-process, so there's often no real-time feedback for the operator. There are also laser line probes, which require attachment to a localizing device. This allows each image to be displayed in its correct position and orientation in space as it's captured in real time. And today we'll focus on those types of probes that can be used in tandem with an articulated arm, the laser line probe with the portable CNN. The process of laser line scanning is very simple. The laser line probe, a non-contact scanner, is attached to a 7-axis Faro arm, and the laser projects a line onto the object surface. A camera captures the profile formed by the laser line 60 times a second as the operator moves it over the surface, and the software determines the location for each point along the stripe. And finally, those points are rendered into a point cloud. A scan with an LLP will produce a point cloud, which is just a large 3D group of points that correspond to the geometry measured. The scans are typically acquired for two main reasons. The point clouds can be exported to CAD and developed into models for downstream use in activities such as design, simulation, analysis, and development. But they can also be used for inspection, which confirms the product's dimensions and can initiate actions such as troubleshooting or corrective action responses. Faro's latest offering to meet the increasingly demanding requirements of people who need portable arm laser scanning capability is the Faro Edge ScanArm, the world's first smart arm. It integrates seamlessly with all Geomagic design and inspection products. An innovative integrated touchscreen and operating system provide true portability in the workspace, and also wireless connectivity via Wi-Fi and Bluetooth, with wired connections also available via USB and Ethernet cable. The lightweight, only 2.7 ounces, and low form factor of the LLP allow obstruction and collision-free measurements to be taken with the contact probe or the LLP, and switching between the two is seamless. And a fast data capture rate of 45,000 points per second means that the object is captured quickly and comfortably by the operator. In more detail, the LLP consists of a laser emitter, a camera, and a separate calibration plate. In close-up, the LLP looks like a spare handle that you switch out as desired with the regular handle on your Faro Edge arm. The laser emitter is a known baseline distance from the camera and is also at a known angle, allowing for easy triangulation of the coordinates for the points captured. The calibration plate allows the operator to simply establish the orientation and position of the laser line probe relative to the Faro arm. And a quick look at the applications. Non-contact inspection allows you to inspect soft, deformable, or complex shapes, perform cloud-to-CAD comparison, rapid prototyping, reverse engineering, and 3D modeling. First article inspection allows you to easily measure and compare prototype parts to nominal data. CAD-based inspection, where you measure directly against CAD data to see real-time deviations from the nominal information. And reverse engineering, where you can digitize a part or object to create a fully encompassing CAD model. That concludes my part of the presentation, and I'll be handing over to Michael, who will introduce you to Geomagic and demonstrate some reverse engineering applications for scanned data. As I've said many times before, the applications for using the data acquired by your Faro Edge ScanArm are limited only by your imagination and your software. The technical handover behind the scenes should only take a few moments, and then you'll see how Geomagic will remove the limits of your imagination and reduce the amount of perspiration required to complete the well-known perspiration-inspiration equation we're all familiar with in product development. Thanks for your attention, and now here's Michael.
As we said, we're going to go through the scan-to-print workflow with a little bit about who is 3D Systems and a little bit of clarification about the names. Many of you probably signed up for the webinar as a Rapidform webinar, Rapidform and Faro. Over the past year, 3D Systems has made strategic software acquisitions, including Rapidform, Geomagic, Libre, and Sensible. And this has very recently been combined into a unique Geomagic Solutions brand. And that's you see that here with the 4 brands turning into one. And so we'll be talking about the products, the way they're offered today, and show you a little bit about the scan-to-print workflow that's enabled by this synergy of different technologies coming together. And we talk about the scan-to-print that basically ends up being 4 pieces. We'll look at only 3 of them today. First is the capture, and you saw a little bit about that in the slides that Les was presenting to you about how to capture information about the real world. Design and modification of those pieces, adding something of your own to something that already exists, and then going to producing, manufacturing, or making something. And today we'll be looking at 3D printing as the output. And then as Les mentioned, there's also inspection after that, comparing what you created versus what you had designed. Talking about design freedom a little bit, in the typical case, you start from a blank screen and you use traditional CAD modeling tools to build your part. But what about physical objects or virtual clay or sculpting, those kinds of tools to help streamline and slingshot your development process along? With the Geomagic Solutions brand, all of these things are just inputs into what you can do by mixing different technologies together. Physical objects are the same as an object you download off of the internet as a pre-existing model, or something that you draw from blank screen, or something that you could virtually sculpt with clay. And then once you have that data, then it's going out to different outlets, whether it's going directly to 3D printing or going to a native CAD application for further use and inclusion into a data family. You want to make drawings for other processes, or manufacturable models for sheet metal or molding, castings, things like that. We're going to take a look at 2 products today from the Geomagic suite. First, we're going to look at Geomagic Design X, which was formerly Rapidform XOR. This is the fastest path from 3D scans to your specific CAD software. And so this features parametric history-based reverse engineering or reverse modeling, and it helps you to create native models for SolidWorks, Inventor, NX, Creo, and those applications. And it enables complex or parts or incomplete scans to be turned into manufacturable designs within your target CAD system environment. Alternatively, we'll also take a look at Geomagic Design Direct, formerly Geomagic Spark. This is the fast and easy CAD modeling from 3D scans. If you don't have an established CAD or PLM system that your data needs to fit into, you can do the entire process in one application with direct modeling-based reverse engineering that's built on top of SpaceClaim. It gives you intuitive push and pull modeling tools, and you can use the scan data like 3D tracing paper to accelerate the process. And then you can go on to 2D drawings, assemblies, and you can also integrate different parts from trace parts and other of the repositories online. Now, of course, there's other products from the Geomagic Solutions group. One of the things that was mentioned in this webinar that we won't look at is inspection there on the right. We have a whole suite of tools, and the slogan here would be the right software for each application. And we're only really going to touch on this one section right here. For a demonstration, we've got a scenario that we created for you to kind of give you an idea of what the process would be like. We've scanned 2 different guitar components with the Faro edge arm. We scanned a foot pedal cover for a foot pedal effects pedal for the guitar, and we scanned a wooden guitar body as well. And we're going to create new models and then add design changes of our own to each of these. So for the foot pedal, we'll take a look at Geomagic Design X, and we'll take a look at how it's possible to create a smart or parametric model. Maybe this pedal would be used on multiple aftermarket pedals, things like that. Instead of having multiple parts, we can have one file that could solve different needs. And for the guitar body, we'll take a look at Geomagic Design Direct, and we will create a customized, personalized design for that guitar body. And then we're going to print parts with the 3D Systems printer. So go complete from the original physical inspiration to new printed parts. So first, using the Faro edge arm, as Les talked about, we were able to scan this wooden guitar body that you can see here. Scanning is very easy and directly integrated into Geomagic Design Direct. We can capture information on a desk, on a shop floor, in multiple areas with the portable metrology. We also scanned this foot pedal cover, which you can now see. That might not have been obvious what it is from me explaining it. This is a much smaller part and a little bit more mechanical. It's a casted component. We obviously won't have to care about a lot of those design constraints with printing. And we scanned this into Geomagic Design X, and we'll take a look at modeling with that. So at this point, we're going to switch to actual software use and take a look at the two products. So this is Geomagic Design X, and this is the scan of our foot pedal here. You guys can see there's probably some delay in rotation, so I'll try to go a little slow. You can see there's some foam was set in here inside this plate as kind of a cushion, and we see there are drafted walls on this, and it's also a very small component. We didn't capture a lot of data, primarily because we don't need to. This is a very simple design, and we're going to design our own foot pedal that we would make and be able to use. And we saw there's some missing data here. So the first thing to do in a parametric kind of sense of modeling is to create 2D sketches and create CAD features from those. So if I create a sketch inside Geomagic Design X, you'll see that I can actually take sections of the scan as I go through here, and I'll use these like digital tracing paper. So I'm given a 2D sketch with this pink outline, and this outline is really what I want to draw. So I have full sketching capabilities like you would find in your native CAD package. The only difference here is that these are being accelerated and sped up by the use of 3D scan data. So I very easily make a sketch, and then I'm just going to start working through this like a regular CAD model, creating the part. I'll add some draft to this to better capture the design and shape. Go the other way a little bit. Again with some draft. And I can set the actual values for this numerically. So this should be 4 millimeters, and I'm just going to go below a little bit. This is actually some foam padding you can see from this side view. I don't need to model in that foam padding. I'm just concerned about the main shape here. And I'm not that concerned about this side either. It's kind of drafted at a very different angle from the rest of the part. I'm not sure what the design intent there was, but I don't have to follow that exactly to create the model that I'm going to print. We can constantly check the accuracy of what we're building versus the scanned part. In the green areas, I can see that it's fitting very well. Red areas are positive material in my model, and blue areas would be negative material. I'm going to add a few more design inputs here. And we'll take a look at optimizing this. I need to kind of step shape that you can see here. So again, I use the scan data as a kind of tracing paper. And I'll build a sketch that will provide me that shape. Just trim things together. And now I have a tool that I can use for a solid cut operation. These are typical CAD tools. Again, they're just being accelerated by the use of 3D scan data. You can have it extrude both ways and cut through the part. Now I'm starting to look like I've got a foot pedal. One of the easiest things to do would be go back into that sketch. We have a full feature. That everything we're doing is being recorded. This is the same as major CAD systems such as SolidWorks, Inventor, NX, CATIA, those types of tools. And the reason for that is that we are going to use that feature tree later to make this information portable. And we can take it to any of the CAD packages that I mentioned to make the whole design completely portable. I'm going to add just a couple more details here so it looks complete. You can see I can fit geometry right to the scan, such as that circle. And I can snap things together, better fit the shape. We won't spend too much time on this. I'll add a couple of dimensions. So instead of 2.43111 something millimeters, I'm going to say the hole is probably intended to be 2.5 millimeters, 2.5. And I can make those adjustments to the design all in one shot. Edit my process here, and you can see that I can change the model that I'm creating. Now I need to hollow the part to create the inside. I don't want to build a huge pedal that weighs more than the whole foot pedal assembly. I'm going to remove a fair amount of material here to create the shape. And again, I've got the 3D scan data here. I can use it to help me define how thick this material should be. So now I've got a 3 millimeter thick foot pedal. The only thing I really need for it to be functional is this post here. This actually presses on a button inside the assembly and actually functions. And I can add that very easily with the process. You can see I can just move the cross section up and down the part by dragging. I'll find a good cross section here. And modeling this is quite easy. Pretty much 2 boxes. I can snap onto this. Finish this design. And then trim away all of the things that I don't care about there. So here you can see I'm just adding in the last functional piece. Even if I just made it like this, 25.35 millimeters, at this point this would be a functional piece. So we can very rapidly go from an existing design to a replacement. And I don't have to worry about the draft or any of the additional features or even the foam just to get a functional model. Now, we did mention customizing this. So if we take a look at the front face here for the pedal, maybe I want to add some text. So I'll add some text for our groups here. And I can just simply emboss that onto my CAD model. And we'll make sure that it's pad. So we'll bring the text off of the face here. Of course, this is a very simple example. We can use our logos, or use some more advanced design tools to further customize this, but we'll look at that a little bit more with the guitar body. And this pretty much gives us a customized foot pedal. And this is a model that we can take with feature tree information into our CAD systems, and there'll be actual sketches and actual extrusions and dimensions that we can modify and edit there. And we'd be able to go to any kind of manufacturing or also just 3D printing as well. But this time I'm going to switch to Geomagic Design Direct and show an alternative route and a little bit more about the customization. Here inside Geomagic Design Direct, you can see we've got the guitar body this is the one that we scan. And I can very quickly extract information. You would imagine I could take a sketch and build this guitar body shape, but it's a little bit more freeform. I don't really have the time or the patience today to actually draw that outline by myself. So I can very easily just select data on the scan. And the selection's very easy. I can roll the mouse up and down to select more or select less. I can use Shift to pick more data. And I'm just going to grab this outline of the guitar body for very fast capture of the shape. A few more areas here. Hopefully the delay for the screen sharing isn't making it difficult for anyone to see what's happening. And as we're selecting the data, the software is also solving what is the profile that would match this shape. We can add additional constraints, such as it needs to be from this direction. Having just a tad of graphics difficulty probably from the webinar. But we won't let that stop us. So here you can see it created a solid block for that shape. And this relatively matches the guitar body underneath. And that was a very quick extraction that I did. Now I can see this kind of circular shape. This tells me that the top of the guitar isn't exactly flat. It's got some curve or bow to it. So what I want to do is extract a quick freeform shape from the top of the guitar, and I'll use that in the modeling to make my guitar match more closely the physical part. So it creates a large freeform shape here. And we've got lots of push and pull direct editing tools here. I'm just going to make the top here a lot taller. We'll split this by that freeform shape on the top and remove the extra material. Now I've got something that looks a lot more like my guitar. If I turn it over on the other side, I can see I'm not quite at the bottom of the guitar. I can push and pull and drag. I can also go up to a specific point on the guitar body and snap directly to that scan. And we'll extract one more pocket here, and then we'll take a look at some customizations and what we can do. If I want to grab this, I can follow the same principle, select that information, and you see that profile that it generates automatically there. Hopefully that's updated for everyone. And that creates a new piece. Now using these direct editing tools, it's very simple and easy to just come in and say, I want to cut that out of the rest of the guitar. And if I want to adjust the bottom of that pocket, I'll just snap it to the scan there. So I've got the basic idea of the guitar shape, but one of the things that I don't have here is the neck. I could cut out a neck profile, which is pretty easy to do. Start with a section, drag that section up, and you can see it cuts through the scan here, much like we saw in Design X. And I can draw in a box, and I can use that to help cut this guitar neck in. Now, I also happen to know I want to use an off-the-shelf guitar neck. So I'm not going to try to match this exactly. This may not match what I want the design to be. I'm just going to use this as a simple placeholder. extrude this up to cut away that material. And I've got a basic shape. I can even go down a little bit as well. And so now what I want to do is turn off the scan, and I'm going to bring in an existing guitar neck component. So this is something that we downloaded from an online part repository. Just flip it around real quick. And I'm going to try to make sure that this guitar will fit this body. So I can quickly use some assembly tools. I want to match that face, that face. I'd like to match the center of this pocket. Make some quick reference plane. I'll match the center of the neck to the center of that pocket. You see it slides over there. And the end of the neck should stop right there. So I can see I've got the neck placed on the model, and I can see that, you know, it's not quite wide enough. I need to adjust the guitar neck to better fit. And again, I can go and edit this in a cross section to make sure that the neck that we're going to buy off of online parts store is going to fit with what we're going to design. So I've got my profile here. I can drag and modify that. Add myself some extra room. Back to the 3D view. Now you can see I've added extra room just for that guitar neck. Now, we were able to really quickly develop this guitar body idea, but this is a very boring guitar body. Nobody should just have some simple guitar body. We can add lots of interesting things to it. I can apply some large fillets to this. Type in a value, I've got a fillet. And we won't spend a lot of time trying to modify this, but the idea is the same. If we want to, we can come in and we can add special features. We can remove material, especially if we're printing. And we could also add some text and things like that. I'm just going to quickly draw an outline. So if I take that shape, I can pull that right through. And of course, I don't have anything to mount, but this gives you the idea of how I can modify this. Now, in our office, we created an additional guitar body, and it's one that we wanted just for ourselves. So we were able to make some pretty drastic changes to it. Lots of removed areas of material, lots of very large fillets. We also applied a model of the 3D Systems logo here. We made the back of the guitar concave, different things like this that we can do with the software, truly making it our own, personalizing and customizing this. And if I go back to the PowerPoint now, the next step would be 3D printing, bringing those designs to reality. And we also have the technology for full color 3D printing. So you get lifelike photo quality models in 3 dimensions. As they say, if a picture is worth 1,000 words, what is a full color 3D printed model worth compared to an image or something like that? So here's some pictures of the result of the guitar that we made. This is the guitar I just showed you. You can see some of the layers being printed in real time over here. And the result is it came out of the printed material. And then the cleaned up result here and then sitting next to the original wooden guitar body there. So this is a good example of being able to take a physical part for inspiration, scan it, modify it, make it your own, and then go to 3D printing to create something unique that truly embodies your vision and your design and your passion. I think that's about all I have.
Okay. Thank you very much, Michael and Les. The next thing we want to do is we have a poll question which we would like you to answer. We're going to have this question available to you for about a minute so that you could make some choices. We're asking you, which of these technologies covered today would you be most interested in receiving more information about? And you can click on any 1, 2, or 3 of the choices offered. And that's choice 1 is 3D scanning for CAD. Choice 2 is 3D scanning for inspection. And choice 3 is 3D printing. And we're going to hold this voting for about a minute, so please go ahead and register your votes. And we will display the information once it's tabulated, and then we're going to go into some of the questions. So if you have already voted and you have a question, please feel free to go ahead and put that into the question box. We already have a few lined up. Okay, the poll has just been closed. And I think you can see on your screen, so 64% of you are interested in 3D scanning for CAD, 71% of you are interested in 3D printing, and the remaining 32% of you are interested in 3D scanning for inspection. So now we're going to open up for the question and answer period. One of the first questions that came in was, could one of you, Les or Michael, please define the leapfrog terminology?
Yeah, I can take that. The leapfrog technology is just a technique that's used to extend the range of pretty much any measuring device. It's just a generic term. In the Faro software, we call it move device position. But essentially what you do is you measure some targets that aren't going to move from the first position, remeasure them from the second position, and use that reference information to tie the first position to the second position.
Okay. Another question that came in here is there a Faro CMM designed or priced for educational purposes for engineering students?
We have educational discounts available for all our products. As an application engineer, I don't keep up to date with all our pricing, but we can, if you contact Faro, we can make that information available to you very easily.
And just as a quick aside, at the end of the presentation, we will have contact information for all of the attendees. Then one of the questions here is, can you create silver and gold jewelry?
The challenge here would be the laser scanning. I'm sure Michael will chime in on the software side in a moment, but the resolution of the scanner that we've showed today is about 0.1 of a millimeter is the minimum distance between points. So if the detail that you're looking to do is getting close to that resolution, then from a scanning standpoint, you'd struggle. But the software, I'm sure, would have no issue, so I'll let Michael give his answer.
From the software perspective, scale and the type of object doesn't really matter. Just like you can design anything from a guitar body to jewelry in a number of different softwares. If you can capture the information that you're looking for with the device, or if you have the design for the jewelry, it's definitely possible to create 3D printed metal-based objects. Typically, precious metals like gold and silver aren't used in the printing process directly, but the alternative is to print a wax pattern, and that pattern can be used for investment casting And that is widely used in the jewelry industry today in many cases.
Okay, a question has come in. Can you scan a person?
There are actually scanners out there that specifically for scanning people. The challenge with using the scanning arm technology that we've used today is that people tend to move as you're trying to scan them. So the technology we've shown today wouldn't be ideal for this scenario, but I have in the past scanned body parts with the scanner, such as ears and other parts of the body.
Okay, what is the smallest part you can comfortably work with in this package?
As Michael said, it doesn't really matter to the to the software, but the level of detail is obviously very important when you're using the scanner. I mentioned in the previous answer that if the detail is down in the sub-millimeter range, then the scanner would certainly struggle to pick up that level of detail.
Okay, and how long did it take to scan the parts?
I guess I can answer that. I did the scanning. It took about 15 minutes to scan that wooden guitar body. There wasn't a lot of details. You can see it's just a couple of pockets that we had to get information inside and then flip it over. The little foot pedal took maybe 20 to 30 minutes because there were lots of undercut areas and small places that we had to try to get inside. And you saw we didn't try to get all of the information in that model. But those kinds of desktop-sized components take somewhere between maybe 15 minutes would probably be the fastest thing that you'd scan on your desktop to an hour. The larger the parts, the more complex, obviously, the time goes up.
Okay, Michael, I think this other question is for you as well. What 3D printer do you use and how much did it cost?
Okay. I get to use the same answer that Les said there. I'm not that familiar with the pricing for the printing equipment. 3D Systems has a large variety of printers, 7 types of printing technologies. What we used here, the color jet printing, the color parts that I made, that is one type of printer that's available, and I believe those have several different models and a pretty wide range in pricing from business, enterprise, affordable to closer to production scale.
Okay. Do you know what the largest size 3D printer you have that can print in full color is?
The largest size color printer is the one that we actually printed this on. I could have printed something that's maybe about 20 or 30% longer, like at the length of that guitar body. That is very close to the width of that printing volume. And then it's also maybe about as tall vertically, like the Z depth as that guitar is tall. So that guitar is a pretty good example. You could put something a little bit more elongated in there, but that's kind of the size if you were lay something flat in the full color printer bed.
Okay, this one is for Les. Can the mesh cloud be brought directly into Creo 2 or SolidWorks 12?
I'm not familiar with Creo 2, and I believe that SolidWorks 12 can sometimes be a licensing or a module issue as to how much data it will actually allow you to handle. So, SolidWorks and the Geomagic products handle most of the industry standard formats. So I'm almost positive that there's a clean way to get the data from one software to another. But the bigger issue is probably the SolidWorks have the horsepower to handle the amount of data you might be considering transferring.
Okay, and this question is from Michael. Oh, did you want to answer that?
Yeah, just opening data in different applications is obviously very different than actually being able to do something useful with those. And I would like to point that out. As Les said, we can send data from any application to any application. You can open a point cloud in Excel. That doesn't mean it's particularly useful to you. So how useful the data is inside that application is probably the thing that's more important than just whether or not it can be open.
Okay. And Michael, this is a continuing question for you. With the 3D printing machine, was there support material that had to be removed?
For this particular type of 3D printing, the full color printing, there's no support material. It's printed in a bed of powder. You might have seen one of the pictures that said it had just come out of the printer. It looked a little white. It had some powder caked on it. It actually supports itself inside that bed of powder, and there's no need for support material. You just have to blow off the excess powder from that part.
Okay. And how was the color mixed for the printer?
It's a great question. I had slides to cover that. I didn't know if anyone would be that interested in it. The ColorJet printers actually use inkjet color, just like the printer on your desk. They're color cartridges in the cyan, magenta, and yellow, I think. And those print into the powder material with the glue binder and create any color print you can. I think one of the specs is that the printer can handle up to 90% of the Adobe standard color palette, so quite a variety.
Okay. I think this one is for Les. Did you need targets, or do you need targets or dots for scanning?
With the handheld laser, the scanners, because it has a localizer that tells it where it is in space, no, you don't need to have targets on the part. Those targets are usually there so that images that are captured in space can be stitched back together because there's no other reference for them. But because the Faro edge arm always knows where it is in space, it tells the camera exactly what it's looking at, and we actually capture a 3D point cloud rather than a succession of 2D point clouds that then have to be manipulated together.
Okay, and again, another scanner question. Will the scanner that you talked about, or any of the other ones that you have out there, will they grab enough detail to replicate a tabletop statue without too much alteration to the file?
Yes, there are a number of universities and artistic establishments and ventures around the country who are making use of the Faro arm to scan objects of the size that you're talking about.
Okay. Can the same point cloud data be used across both DesignX and Qualify?
That is correct. Once something's been scanned, the data is pretty universal. It can be used across any of the Geomagic product suites.
Okay. And this is back to the leapfrogs question. How many leapfrogs can you successfully execute?
Whenever you carry out a leapfrog, because you're measuring artifacts and then remeasuring them from a different position, there's a potential for a build-up of error. It's very, very difficult to quantify because every situation is different, but really you have to look at the tolerances you're trying to hold and look at the error accumulated by every leapfrog as you go and see if it's acceptable. Ideally, in the best possible case, you'd want to scan from one position, but sometimes it's impossible or just not realistic.
Okay. And this question comes in, do you need an engineering background to use the software?
I would definitely say that it helps, but we also have many customers that have no 3D software experience beforehand. Picking up the software, learning it, and using it to create or recreate all kinds of things. So, as you saw with both DesignX and DesignDirect, they're very CAD-centric tools. Having a experience and understanding of how to use CAD tools, whether from another package or not, obviously gives a good baseline for how to go about creating the models, but that's something that can be learned it's just a matter of how much time.
Okay. And this question is, on the last slide, what was the difference between the rough white body on the left, this is for the guitar, versus the finished color body on the right?
That's exactly what I was talking about with the powder material. The white body on the left was actually the guitar body with the powder still caked around it. So just pulled out of the bed of powder with still some of the material packed on it. We just use an airbrush. It's a part of the machine, actually, which is the separate compartment of the machine, to just blow off all of the excess powder material from the part. That's the only difference.
Okay. What materials do your printers currently support?
That's a pretty detailed question. I know that we can print in wax, plastics, resins, the full-color powder material, as you saw in the example here today. We can also print nylons, and as well as ABS plastic, and we do some metal laser sintering, laser melting for metal printing. But I'm not sure exactly what kind of metals we do that with.
Okay. Les, this is for you. Are the lasers on the scanners, are they safe for your eyes to look at them directly or indirectly?
The laser scanner laser was specifically chosen because it's categorized as eye safe. Because the laser is spread out as a line, it's much less intense than looking into something like a laser pointer, for example. Just because something's eye safe, it doesn't necessarily mean that you should look at it directly. What it means is that if you look at it, it automatically triggers the blink response from the eye, and the eye will automatically close before any damage can occur. So yes, it's eye safe, but you should always take precautions when you're looking to scan in the region of somebody's eye.
Okay. What are the system requirements to use the Faro laser scanner, DesignX, and Pro E on one computer?
The post-processing is probably the most intensive part of it. The laser scanning itself does use the graphics card, but the most intensive operations are probably done by the post-processing software. So Michael's probably best placed to answer this question.
Yeah, a machine that's set up to run a product like Pro E or Creo or SolidWorks or Petito or something like that well, generally will work very well for the type of scanning process that we're looking at today. In general, the scan data is very resource intensive, as Les mentioned, but we do as much as we can to try to reduce the burden on the machine, which is different than what would happen if you open the scan data directly into your CAD system. But a good graphics card is always good for any kind of 3D software, and the more memory you have, usually the merrier.
Okay, we have time for a couple more questions. A lot of them have been asked, and if we don't get to your question, you'll notice on your screen you have contact information for both Les and Michael, so feel free to email them, or in Michael's case, to call him with some of your questions if we don't get to them. Let's see, one question that's here is, what is the accuracy of the scanner, and how much deviation do you get once you move it into the DesignX software?
The accuracy of the scanner is about a thousandth of an inch, and when it's mounted onto the arm, that adds another just over a thousandth of an inch to the accuracy. But there are so many different things that come into play. How well is your part fixtured? What is the surface topography of the part? What color is it? How shiny is it? All these things can come into play with the scanning and give you the system accuracy that's defined, or a reduction in that. But often when you're scanning a part that isn't perfect anyway. What you're trying to do is characterize that surface so that then, using the software, you can create the nominal model that you need. And Michael can probably add more to that.
Les is exactly right. Once the data has been captured by the hardware device, we more or less consider that to be gold or perfect. And how closely what you're drawing matches that scan is totally up to the user. You saw in the Design X there was some color mapping, different colors showing me how it was fitting, but you could see that I was able to draw anything that I wanted. I could make changes. It's up to me to determine what's critical to have exactly the way it is physically, and what are things that I can have more idealized. For most parts, there's a good example that if there's a flat area where it should sit on another face or a table or something like that, physically that part isn't actually flat. All the way down to microns, nothing is actually flat. And it comes down to, do you want to have some slight bow that might be present in your physical part, whether it's molded or cast, there's always warpage kind of issues. Or do you want to design something that should be flat, that's going to work in an assembly and things like that? So those things usually end up being a trade-off over what needs to be super accurate for some sort of fitting or something like that, and what do I know should be round or should be flat, those kinds of design intent decisions that the user makes.
Okay, is there any form of automatic feature recognition available in Geomagic for CAD model generation?
So I guess I'll say the idea of a totally automatic modeling from scan data is kind of the silver bullet. We're always working day and night towards that goal, but nobody's there yet. The scan data, we have a couple of factors there. I just talked about how the part is imperfect. That actually has a lot to do with it. The scan actually isn't perfect. So it's not entirely, even the best feature recognition, which we're doing, we're not sure if that's meant to be a plane or it could be some sort of freeform surface. There has to be some user involvement at that point. The machine can't make a decision for you about what the design should be. And so what we try to do is give the user the tools to impart that knowledge along with the scan data to get the best result. And we try to speed everything up as much as we can. We can identify pockets and revolves and stuff like that, but it's ultimately up to the user to interactively go through this. If we just tried to have it make a CAD model, I'm pretty sure somebody would say it's not the right choice, and that comes down to this human decision making.
Okay, and one more question. Is there any need for another CAD software package besides a version of Rapidform?
So that's a question that we get fairly often. As you saw, there are two products I presented to you today. The one, Design X, is specifically designed to be a bridge to go from the Faro device to a native CAD system. So it's going to help you create the features and then carry those features directly into SolidWorks or something else. Design Direct is possibly a little bit more independent. It doesn't have to go anywhere else. It can make drawings, stuff like that. It's definitely not a most ideal CAD solution. There are several lower cost solutions for traditional CAD design. These are specialized for capturing physical parts and moving to the design space.
Okay. Now there are quite a few more questions that we have not had a chance to get to. As I mentioned before, you will see the contact information still on your screen for both Les and Michael, so feel free to send them your questions if you still would like to have them answered. And Les and Michael, thank you so much for a very informative webinar. Just a reminder for everyone, this webinar will be available later on at designworldonline.com, and we will also send you a URL link to the webinar. You can continue to have a conversation about this on Twitter via the hashtag DW webinar. And don't forget, you can also continue this conversation on engineeringexchange.com, or you can connect with other Design World social media venues, including Twitter, Facebook, LinkedIn, and YouTube. Thank you both again for a great seminar.